In this video, we're going to, as you can see from the SWABOT, students will be able to evaluate a definite integral using the fundamental theorem of calculus. Up until this point, to evaluate a definite integral, we have used, let me change colors here, we have used basically geometry. And to evaluate that, we have done counting blocks, and we have done Riemann sums, and we've done the trapezoidal rule, and we have done the definition of a definite integral, but we have not evaluated definite integrals analytically, and that's what we're going to do today, or in this video. So, if you are in my class, please stop the video and do this warm-up, and believe it or not, this warm-up will lead you to a little aha experience about how to evaluate a definite integral analytically. So stop the video, do the warm-up, have your little aha experience, and then play the video and see if the video confirms what you found for yourself. Notice that we've been given a velocity function, 3t squared minus t minus 4, and first of all, you've been asked to find the position function, s of t, if s of 2 is equal to 8. So we know that s of t is equal to the antiderivative of v of t dt, which will give me t cubed minus t squared over 2 minus 4t plus c, but we have a particular value, so we can substitute in 2 and get 2 cubed minus 2 squared over 2 minus 4 times 2 plus c, and that's equal to 8, so that'll give me 8. 2 squared is 4, divided by 2 is 2, minus 8 plus c is equal to 8. So the 8 and the negative 8 subtract out. C is equal to 10 if I did my calculations correctly. Let me just double check that. My integration, t cubed, 3t cubed over 3, which is t cubed, t squared over 2, minus 4t. The signs are correct. Substitute in 2. 2 cubed is 8. 2 squared is 4 over 2 is 2. And 4 times 2 is 8. Add 2. Okay, so s of t is equal to t cubed minus 1/2 t squared minus 4t plus 10. All right, hold on to that because we will need it a little bit later. Write an integral that represents total displacement. The key word here is displacement. Remember, displacement is a measurement of net area accumulated under velocity curve. We're starting at 2 at 7, starting at 2 and stopping at 7, and we do not want to change the sign of any of those areas. So this would simply be the integral from 2 to 7 of v of t dt, and that would give me the total displacement of the particle. Not knowing whether there's negative area, positive area, that doesn't really matter for displacement. Letter C, write an integral using absolute value to represent the total distance traveled. Again, we have not looked at this function. Maybe all the area is already positive, and maybe the distance is equal to the displacement, but we don't know for sure. So if I'm going to collect the total distance traveled, I'm going to start at 2, stop at 7, and I'm going to force any negative area to be positive. Now make sure when you do this that the absolute value goes around the function. You're forcing the graph, the function, to be positive. So this would represent the total distance traveled by the particle. Letter D, write an integral without using absolute value to represent the total distance traveled. So to do that, if we're going to do this without using absolute value, we're going to need to know when and where the velocity is positive and negative. So the first thing I'm going to do is I'm going to set the velocity function equal to 0 so I can test out the regions. So velocity is 3t squared minus t minus 4. So 3t squared minus t minus 4 equal to 0. Let me make sure I copy that correctly. Good. So 3t and t and 4 and 1 and we want the t to be negative, positive. Let me check myself here. Negative 4t plus 3t gives me negative t. That'll give me negative 4. So t is equal to 4/3. T is equal to negative 1, and we're going from 2 to 7. So negative 1 is not on the interval from 2 to 7. So from 2 to 7, 4/3 is not on the interval either. 1 1/3, so let's get rid of that. Okay, so neither of these is on the interval. So there may be some regions of positive area and negative area throughout the graph, but neither negative 1 nor 4/3 is between 2 and 7. So between 2 and 7, I'm going to pick a number. Still got to do a number line. So here's 2, here's 7 v of t. I'll substitute 3 into the velocity function. And if I substitute 3, that'll give me a positive, which is positive. So all of the area is positive. The particles moving to the right or up, depending on the reference. So write an integral without using absolute values. So that would be the area from 2 to 7, of v of t to dt. In other words, in this interval, the displacement and the total distance traveled are equal to each other because all of the area is positive. So let's take a look at a graph of the velocity function just to verify that. Here I've already put the velocity function into my calculator, and I have adjusted the window to go from 2 to 7, and you can visually see that all of that area in that region is positive, so that the total distance traveled and the displacement would be equal to each other for that particular region. All right, letter E asks us to find the displacement of the particle from 2 to 7. Now, remember, back up in the beginning, we already found a function for the displacement, and displacement is change in position. So if we're going to go from 2 to 7, then we need to find s of 7 minus s of 2. Now to do that, I'm going to put the position function into my calculator just to make it easier to calculate. So I'll have x, move that up, x cubed minus 0.5 x squared minus 4x plus 10. And I'm going to go to the home screen, and I'm going to clear the home screen, and I'm going to do vars, y bars, function, y number 2 of 7 minus, those of you who have the newer calculators, hopefully you know how to access these function names more easily. And we get a total distance traveled of 337.5. Okay, now, what I want you to consider is that how did we get the position function? Well, the position function we found by, I've got too much stuff on the board here. Let me clean up a little bit. Get rid of this. Okay, to find the original position function, we found the antiderivative of v of t dt. We wrote a statement for the displacement of the particle in letter C, or letter B. The displacement of the particle was 2 to 7, and we just actually calculated the displacement of the particle to be 337.5. So, notice what we did. We substituted the upper bound in the position function and the lower bound, thus telling us that if we want to find the displacement, we find the antiderivative of the velocity function, we evaluate it at the upper bound and evaluate it at the lower bound. This is the fundamental theorem of calculus. So it's the analytical approach of evaluating definite integrals. Now I'm going to go back to my calculator, and I'm going to Math 9. I'm going to integrate the original function, y vars, y1, in terms of x from 2 to 7. Uh-oh, there's a problem, Houston. Let's see what it is. Okay, I paused the video and I found my mistake. My mistake was when I typed in the position function, I typed in the wrong sign for the second term. So I do want you to see that when I went back and reevaluated that y of 2 minus y2 minus y2 of 7 minus y2 of 2 is 292.5. So, good, they do agree. So the fundamental theorem of calculus is true. We have not disproven it, and we're not going to go down in history in a calculus book for disproving the fundamental theorem of calculus. So notice when I integrated the velocity function, the area from 2 to 7 is 292.5. And when I substituted into position function and found change in position, I got 292.5. So the bottom line, thank goodness, in general, the antiderivative of v of t dt is s of t. In other words, when you find the antiderivative of velocity, you get back to position. That's an indefinite integral. And in that case, there would be a plus c, and hopefully you would be able to solve for c. Letter G, in general, the definite integral of v of t dt, first of all, that's going to yield displacement, and displacement is change in position. The word change connotates subtraction, so that's going to give me s of b, upper bound, the position evaluated at the upper bound, minus the position evaluated at the lower bound. And then in general, not just on a velocity function, but any function, when we find the antiderivative of little f, we go back to the original function, which is big F. We evaluate the original function at the upper bound minus the original function at the lower bound, and this is the fundamental theorem of calculus. This is how we analytically find or evaluate definite integrals without having to use areas. All right, let's take a look at a few examples quickly. In number 1, we're going to evaluate the definite integral from 2 to 7 of 3. So step number 1 is to find the antiderivative of 3, which is 3x. Now notice, watch how I write this. I find the antiderivative, and then I say I'm going to evaluate that from 2 to 7. Now some books will show it like this. They'll just put the antiderivative, they'll put a bar, and they'll go from 2 to 7. I just want you to be familiar with if you see that. So step number 1 is to find the antiderivative. Step number 2 is to evaluate the antiderivative at the upper bound and subtract the antiderivative evaluated at the lower bound. So that gives me 21 minus 6, which is 15. That is the analytical approach. Now we could prove that geometrically. We have the function y equal to 3. We're starting at 2 and we're stopping at 7. So we have the distance 5 here. We have a rectangle that's 3 units high. 3 times 5 is an area of 15. So that just shows that the geometric versus the analytical approach, you're going to get the same answer. All right, let's take a look at number 2. Change colors here. Step number 1 is to find the antiderivative. So I get negative 3v squared over 2 plus 4v evaluated from 2 to 5. So I'll have negative 3 times 5 squared over 2 plus 4 times 5 minus negative 3 2 squared over 2 plus 4 times 2. So that'll be 5 squared is 20. It'll be negative 75 over 2 plus 20 minus, be careful with these minus signs, 2 squared is 4, divided by 2 is 2, that's negative 6. 4 times 2 is 8. So that gives me negative 75 over 2 plus 20. Negative 6 plus 8 gives me 2, so that's minus 2, so that's negative 75 over 2 plus 18, which is negative 75 over 2, plus 36 over 2, just getting a common denominator, which gives me negative 39 over 2. Let's see. Let's blah blah blah. What do I want to do? Let's go ahead and do them. All right, number 3, I'm going to, step 1, find the antiderivative. So that gives me 3x cubed over 3, or just x cubed, plus 5x squared over 2, minus 4x, evaluated from 1 to 3. So that'll be 3 cubed is 27, plus 3 squared is 9, that's 45 over 2, minus 12, minus, be careful, put a parenthesis when you're doing the lower bound. 1 cubed is 1, plus 5 over 2, minus 4. That gives me 27, 17, 15, plus 45 over 2. I just added the 27 minus 12. Minus 1 and negative 4 give me negative 3 plus 5 halves. 15 plus 3 gives me 18. So I did the change. 45 minus 5 gives me 40 over 2, and that's positive 40 over 2, which is 20. And 20 and 18 gives me 38. You just got to be careful. And hopefully I didn't make an arithmetic error. Number 4, find the antiderivative. You get u squared over 2. Now remember, 1 over u squared is u to the negative 2. So increase the power by 1 and divide by the power. So that would be u to the negative 1, increase the power by 1, and divide by the power. Divide by negative 1 makes that plus 1. From negative 2 to negative 1, which is the same thing as u squared over 2 plus 1 over u from negative 2 to negative 1. So upper bound, that would be negative 1 squared. That's 1 half minus 1. I'm substituting negative 1. Subtract the lower bound. That'd be 4 over 2 is 2 minus 1 half. 1 half plus 1 half is 2 halves, which is 1. And negative 1 minus 2. Negative 1 minus 2 is negative 3. 1 minus 3 is negative 2. You can let me know if I did arithmetic wrong. I'm not taking the time to go back and check these right now. I'm kind of doing them on the fly, so bear with me if I make arithmetic errors, or you can let me know and I'll try to edit the video or put in a correction. In number 5, the big deal here, and I'm not going to keep evaluating these, you get the idea, but we're going to need to start by rewriting this as, well, we can take the square root of 2 out front. Remember, that's our property that we recently learned. And then we'll make this x to the negative 1/2 power from 1 to 8. So when I find the antiderivative, I'll keep my square root of 2 out front. I'll find the antiderivative by increasing the power by 1, which will give me x to the 1/2 divided by 1/2, which is 2, from 1 to 8, and then I'll have the square root of 2 times, and then I'll evaluate the 8, and then I'll evaluate the 1 and do the arithmetic. And lastly, in number 6, the big deal here is I'm going to take the 1/2 out front and get it out of my way. I'll have x minus x squared over x to the 1/2 power. This is just a lot of algebra from negative 8 to negative 1. That'll be 1/2. Notice I'm doing a lot of preliminary work before I even try to apply the fundamental theorem of calculus. That's the same thing as x over x to the 1/2 minus x squared over x to the 1/2, just doing a little 4th grade fraction work. The 1/2 is still up front. It's still from -8 to -1. When I simplify that, that gives me x to the 1/2 minus x to the 3/2 dx. And now I'm going to find the antiderivative and sub in the -8 and the -1. Bottom line, be very careful in the arithmetic and all of the fractions and evaluating. Let's see if there's anything else I want to say about this. You'll get your homework in class. So, if you need to watch the video again, take a look. If I made mistakes, feel free to let me know, and we'll put in some edits on the video.